My name is Michael Rudin. I'm Vice President of Rudin Management Company. I'm fourth generation to be working in the family business. We're based here in New York City, as Vincent mentioned, and own and operate 15 million square feet of buildings here in Manhattan. We own, We own 10 million square feet of commercial properties spread over 16 buildings located primarily in Midtown New York and downtown Manhattan. And we own about 5 million square feet of residential properties comprising 2,500 units, primarily focused on the Upper East Side and Upper West Side of the city. We're a fully integrated management and development company. We do everything in-house, from leasing to operations to management to safety and security, and pride ourselves on the position we take of being forward-thinking when it comes to sustainability and technology and adapting those new technologies into our properties. As Patrick and Kelly have both mentioned, a lot of the buildings that are already on the earth today are over 50, 60, 70 years old. I think by 2050, 80% of the buildings that will be here have already been built. So it's very important to not just apply these new technologies to new buildings, but also to the buildings that are currently existing across the globe. So before I get into DiBOSS, I'll give you a little backstory of how we got to where we are today. How many of you were in New York in August of 2013? How many of you were in the Northeast in August of 2013? So for the few of you that were here, I assume you remember the massive blackout that rolled through the entire Northeast of the United States. As I would assume most of you are involved in some sort of realm of tall buildings, I can assume that most of you know that when a blackout occurs in a building, the biggest problem for the owner or the operator or the management company is people getting stuck in those buildings, in the elevators. Hundreds of people getting stuck in elevators across New York City, and as I mentioned, throughout the Northeast, causes a great headache for not just my company, but for all the various building owners and operators here in New York. When you have an elevator stuck in a building, it's not a simple snap and the doors open. It's many man-hours getting those elevators to the nearest floor. Sometimes you can have an elevator stuck in a blind shaft. So it's obviously a not great situation for the people stuck in those elevators, but for us trying to get those people out, it's also a pretty tough situation. So in 2008, we were asked by Con Ed, who's the local utility provider here in New York City of electric and steam power, to be the landlord representative for an application to the Department of Energy for a smart grid project. And in one of the original meetings we had with them, they asked us if, back in 2003, if a 45 to 60 second heads up about an impending blackout would have made a difference. And obviously, we turned to them and said, well, of course, we would have been able to recall our elevators or some of our elevators to either the nearest floor or the lobby and reduce the number of entrapments that we had in those buildings. And if you extrapolate that across the entire city and across the entire area that was affected by this blackout, you would have saved not only the people who were stuck in those elevators, but the people who were trying to free them, the fire department, the elevator companies who had to come on site to free those elevators. So that got us thinking about how we could build a system that went beyond a typical building management system. Both Kelly and Patrick spoke about the building management systems that are operational in the ICC, the various buildings that United Technologies is involved with across the world. We have building management systems in all of our buildings, but we looked for something that would go beyond that and would allow the various systems within a building to be able to not just analyze or provide data and record data of what is going on with the various systems, but also to analyze that data, understand that data, learn from that data, and to be able to better and more efficiently operate and manage our buildings, and to make proactive as opposed to reactive decisions when it comes to operating our buildings. So from that journey, we created DiBOSS, Digital Building Operating System. As I mentioned, DiBOSS ties in the various systems within the building that you see here on the bottom row. It ties them all into a systems integration facility and up into layers on machine learning algorithms that we used from the Columbia University Center for Computational Learning Systems here in New York City. And what that gives us is a smart property management system output, allowing our building operators, our executives, and any other relevant people the tools that they need to be able to, in real time, anywhere they are in the world, the access and information to make better decisions within their buildings. So this is a snapshot of my company's portfolio. What you see here is the executive view. It shows on the left-hand side the various buildings that are active with the DiBOSS system, and across the right-hand side are the various systems within those buildings that are being monitored or engaged by the DiBOSS system. This can be customized to include as few or as many buildings within a portfolio or management system that are necessary. Clicking on either one of those buildings or one of the various subsystems will take you to a variety of different pages. This system works best when it's shown with a live demo. Unfortunately, we're just going to have to show you some screenshots here. So what you're seeing here is the forecast versus actual electricity usage in a building. This is for 345 Park Avenue, my family's largest building, 1.8 million square feet, located 51st and Park Avenue, just a few blocks away from where we are. It was built in 1969 in an age when technologies within buildings are much different than they are today. And this chart here is showing the actual electrical consumption on a given day in the building. Your typical bell chart started up in the morning. The red line on your left is the building startup time. The greenish blue line on the right is the building ramp down time in the afternoon. And as you can see, in a typical building, when people start coming in around 7:30, 8 o'clock in the morning, and the building starts to become occupied, the electric consumption, as the steam plants, the chiller plants, the HVAC units are all ramping up, so does that electrical consumption. So the green line shows what was the actual use of the electrical consumption in the building prior to implementing the DiBOSS system. Overlay that with our occupancy module, which tracks the inbound and outbound people coming into the building. Again, we have the red line on the left showing the building startup and the blue line with the ramp down. And as you can see, beginning at 8 a.m., as the building starts to become occupied, your typical, what we thought was a typical bell chart. And probably intuitively that we didn't notice to think about was the lunchtime dip in the middle of a day. Most tenants, most occupants in a building will go out and grab lunch. Some will stay at their offices. But as you can see, a pretty significant dip in the overall occupancy of the building from about 11 a.m. to 1 p.m. Once we began to realize that this dip in the middle of the day was occurring and how many people exactly we were seeing leaving the building, we began to implement ramp downs, mini ramp downs in the middle of the day with our steam plants or chiller plants to reduce the electrical consumption within the building. As you can see from the bottom chart here, the load profile, which if you remember before was a typical bell, is now what we call the double humped camel. So in the middle of the day, we're seeing anywhere from 600 and 700 kilowatt reduction during the lunchtime. If you add that onto the more precise startup and ramp down times of our buildings, you're looking at over 1.5 times that amount. We've also, throughout our buildings, deployed sensor. Kelly talked about sensor technology and the increase of sensors throughout the built environment. On every quadrant of every third floor in our buildings, we've deployed temperature sensors to understand and read the actual temperature within a space on a building. As you can see here, the yellow band is what we are prescribed to provide, the temperature we're prescribed to provide our tenants per their leases. And the green band in the middle is what we consider an optimal temperature range. It's between 72 and 75 degrees Fahrenheit, which would be somewhere in the high 20s to low 30s range Celsius. As you can see, the red line again showing the startup of the building in the morning. Those floor sensors are reading much higher. This must have been on a summer day. And by 8 a.m., when the systems ramp up, those floor sensors are now reading the temperatures of those spaces, which have now started to cool off because of the system being activated. This screenshot is what a typical building operator will be able to see in real time, whether he is in the building room, the engine room within the building, whether he is walking the building to respond to some sort of maintenance request, or whether he's outside of the building for some reason, whether he's across the world for some reason. No matter where the building operator is in the world, he or she will be able to see this information in real time and be able to make educated decisions. So if, for example, one of these lines was reading outside of this prescribed band, he would be able to make the adjustment in real time or ahead of time if he sees a floor or a quadrant is moving in the wrong direction. This system is also applicable to the steam demand we have here in New York City. Not many other cities across the world use steam as a form of energy. Most large city buildings here are powered by steam, at least in some part. Steam is a big cost when it comes to operating expenses in a building here. So again, as with our electrical consumption, we're able to drive down the steam demand within our buildings. As you can see, the blue line or the green line is showing the actual versus what the forecast is. Any difference between the two lines is a savings in operating expenses. The machine learning algorithms within this program are beneficial for a variety of reasons. Kelly was mentioning them in United Technology system, but what it does is it allows our system to learn and use historical data, forecasted data, historical weather data, forecasted weather data, as well as all the information that we've taken from our building management systems to analyze and predict the various aspects of a building on a daily basis, and to provide a real-time, on a daily basis, startup time for every building based on the temperature and the forecasts, as well as a ramp down time. So we've shaved our operational days, something that Patrick discussed earlier at the ICC. Shaving the operational day on a yearly basis has resulted in a huge savings across our portfolio. And again, reducing that ramp down time in the afternoon to a more precise time of day, as opposed to what the historical information was that our building engineers and operators were going off of. The system is also applicable to tenants. We as landlords are only responsible, again, this is probably or somewhat unique to New York City, but we as landlords are only responsible for the base building systems within our buildings. The tenants are responsible for the rest of the consumption that they take in their spaces. On an average building, base building systems equate to roughly 40% of the total pie, and tenant spaces equate to about 60%. So when looking at our portfolio, we know that we can drive the 40%, but we also wanted to be able to give our tenants a tool so that they could drive their 60% of the pie and help reduce their consumption as well. What you're seeing here is a daily chart over 7 days for two separate floors. The top chart is the second floor, the bottom chart is the fourth floor. They are identical floors in size. They are identical floors in tenant occupancy. The only difference is that the second floor was built in 2008, and the fourth floor was built prior to 1995. So completely different installations. And this just gives a quick snapshot for us particularly, but for also our tenant, as to how they can better analyze when and how they should implement renovations within their spaces to help reduce their electrical consumption and operating expenses. So as you can see on the new floor, the peak load is equal to the base load of the old floor. If you think about that in terms of electrical consumption and operating expenses, it's a pretty stark contrast for any tenant to see that if they spend some money retrofitting LED light fixtures were talked about, other types of systems to reduce electrical consumption on a floor. It doesn't have to be necessarily physical construction materials, but any type of upgrade in their facility can result in very meaningful savings. Some case studies of our properties. The first two buildings that we piloted the system in beginning in 2012, 345 Park Avenue, which I mentioned before, 1.8 million square feet, 560 Lexington Avenue, a block away on 50th and Lex, about 350,000 square feet. These two properties represent the high and the low end of the spectrum in terms of property size within our portfolio. Also built in different eras, 345, as I mentioned, in the late 60s, 560 Lex was built in the mid 80s. And again, based on their size, have varying mechanical and electrical systems within the building, so gave us a good baseline for the two different types of buildings and the range that we could expect to see. Electricity saved in 2014, 757.5 million kilowatt hours in 345 Park, 2.5 million kilowatt hours in 560 Lexington Avenue. Electricity saved on an average year-over-year basis, 7% at 345, 9% at 560 Lex. Total energy savings, over $1 million at 345 Park. That's obviously a very meaningful number when it comes to operating expenses, as any landlord or management company can realize. $308,000 in 560 Lexington, right around $1 a square foot, maybe a little less, a little more. Emissions saved, almost 3,000 metric tons of carbon emissions between the two buildings in 1 year. That's obviously a great number to be able to tout when talking about sustainability initiatives. Just a quick note on cost to implement the system. About $500,000 at 345 Park, just under $300,000 in 560 Lex. And resulting in a payback of under 1 year within both buildings. Today, we have the system operating in 11 of our commercial buildings. By the end of the year, or beginning of next year, it will be operational in all 16 of our office buildings. And we've also begun piloting it in 2 of our residential buildings to see how the system works in what we like to call dumb buildings. Obviously, residential buildings, especially those that were built before 1970, have much less complex mechanical and electrical systems. So we're rolling that out now and seeing how this system is applicable to that space.